Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly, let me know in the chats if all of you can hear me. If I'm perfectly audible and visible to every one of you. Quickly, let me know in the chats with some fire emojis. If all of you can hear me, if I'm perfectly audible and visible to every one of you. Good evening everyone, good evening. Let me know quickly in the chats. Yes? I think, yes, I am perfectly audible and visible to everyone. So my dear students, as you all must be knowing, today it's going to be our fourth session from the chapter mole concept, right? As you know, we have started one series over here on YouTube, wherein we are dealing with every chapter in detail, right? All the theory, all the problem patterns, in depth, we are studying every single thing. Right? We know we have got a lot of time left till the NEET 2025 examination, and that is the reason why we are studying every single chapter in depth, in detail. Yeah? So I hope you remember the last topic which we discussed in the chapter, that was stoichiometry, right? And in the last session also, we discussed about the stoichiometry in sequential reactions as well. Perfect. So in the today's session, what all things we are going to cover? Let me tell you, today we shall be starting with one of the most important topics of the chapter. And you know it already, the name of the topic, that is limiting reagent. This is one of the most important topics of the chapter, mole concept. Yes. And guys, this particular topic is almost used, I would say, everywhere in your physical chemistry. Right? This particular topic is used everywhere in your physical chemistry. So let's get going. Let's get started with the topic, that is the limiting reagent. I would want you guys to take a note of every single thing, whatever I'll be writing on the screen. Yeah? Yes, whatever we are teaching right now in this particular course, it's more than sufficient when it comes to your NEET 2025 examination. Yeah? All right, people. So, first of all, how do we exactly define the term limiting reagent? Let me write the definition first. My dear students, limiting reagent, it is defined as that reactant. It is defined as that reactant which gets completely consumed. That reactant which gets completely consumed earlier in the reaction. Earlier in the reaction is something which we call as the limiting reagent. That reactant which gets completely consumed earlier in the reaction is something which we call as limiting reagent. And the other one is called as the excessive reagent. And the other one is called as the excessive reagent. Now, what is meant by all this stuff? What is meant by exactly the limiting reagent? Right? What is the meaning of the term limiting reagent? What is the meaning of the term excess reagent? What all types of questions can be framed out of this particular concept? Yeah? Let's try to understand it in detail, guys. For example, imagine that I've got a reaction in which A and B are the reactants, and these reactants are supposed to react and form the product C and D. Let's say this is the reaction. Okay? Let's say this is the reaction wherein A and B has to react, right? And when A and B will start reacting, they will lead to the formation of C and D over here, right? My dear students, first of all, you must be knowing this particular reaction, it will be taking place in a container. Let's say this is the container wherein the reaction will be taking place. Okay? Let's say this is the container wherein the reaction is going to take place. First of all, if I write time t is equal to 0, if I write time t is equal to 0 over here, what is meant by the term time t is equal to 0? My dear students, remember one thing. At time t is equal to 0, it means that reaction has not started yet. Reaction has not started yet. Reactants have not reacted yet to form the products. Okay, that means time t is equal to 0. Time t is equal to 0 means that the reaction has not started yet. Reactants have not started reacting yet to form the products. Okay. First of all, I'm assuming at time t is equal to 0. For example, I've got 10 moles of A in the container. And for example, I've got 5 moles of B in the container. Let's say at time t is equal to 0, we have got 10 moles of A in the container and 5 moles of B in the container. Since the reaction has not started yet, these reactants have not started reacting yet, therefore, number of moles of C as well as number of moles of D in the container at time t is equal to 0 will be absolutely 0, right? As simple as that. As simple as that. Since the reaction has not started yet, so number of moles of products initially is going to be 0. Now, my dear students, what is going to happen? As the reaction starts, as these reactants start reacting, what will happen eventually? I'll say as the reaction starts, number of moles of reactants, they will keep on decreasing with time, and number of moles of products will keep on increasing with time. As the reaction starts, as these reactants will start to react, what will happen? The number of moles of reactants, right? It will decrease with time, and the number of moles of products will start to increase. Okay? Right? Why it happens basically, say, initially you took 10 moles of A, you took 5 moles of B, right? You had 0 moles of C and 0 moles of D in the container. Now, when the reaction starts, that means these moles of A as well as moles of B, they will start to interact with each other. They will start to react with each other and will lead to the formation of products. So eventually what's going to happen? When the reaction starts, the number of moles of reactants are going to decrease with time, and the number of moles of products are going to increase with time. Can I say, since the number of moles of reactants are decreasing with time, can I say out of these two reactants, there will be one reactant which will completely get consumed in the reaction? Yeah, I can say that. We know as the number of moles of reactants keep on decreasing with time, right? Number of moles of reactants keep on decreasing with time. I'll say out of the two reactants, there will be one reactant which will be 100% consumed earlier in the reaction. And that particular reactant which will be 100% consumed earlier in the reaction, what do you call that as? You call that as a limiting reagent, right? Yes. My dear students, I'm assuming B is the one which gets completely consumed in the reaction. Initially, you had taken 5 moles of B. What you'll observe after some time, there will be 0 moles of B in the container, right? So that reactant which gets completely consumed earlier in the reaction, what do you call that as? You call that as limiting reagent. If B is the limiting reagent, what should I call this A as? A I'll be calling as excessive reagent. A I'll be calling as excessive reagent. My dear students, when this B would have got completely consumed, when there will be 0 moles of B in the container, what you will observe at that point of time? Still you will observe some moles of A in the container, right? Because A is excessive reagent. Out of 10 moles of A, there will be some moles of A still left in the container. And similarly, some moles of C and some moles of D would have got formed, right? And let me tell you one more thing. When one of the reactant gets completely consumed, right? When B gets completely consumed, there will be no B in the container, but there will be some moles of A in the container. But with those some moles of A which are left in the container, there are no moles of B to react. So the reaction would have stopped, I believe, right? reaction would have stopped at this particular point of time. Perfect. So in short, what is the limiting reagent? I would say that particular reactant which gets completely consumed earlier in the reaction, that's what we call as limiting reagent. And the other one I'll be calling as the excessive reagent, right? Point number one. And when one of the reactant gets completely consumed, the reaction stops at that time, right? No doubt, there will be excessive reagent in the container. No doubt, there will be some moles of A in the container. But with those moles of A in the container, there will be no moles of B to react. So the reaction would have stopped. Yes? Remember one more point. My dear students, limiting reagent is the one. Limiting reagent is the one that decides the entire product formation. Limiting reagent is the one that decides the entire product formation. For example, if I ask you, how many moles of C have got formed? How many moles of D have got formed? How many moles of A are left in the container? All the information is decided by what? Limiting reagent. So limiting reagent decides the entire product formation, right? And the same limiting reagent decides the amount of excessive reagent left in the container as well. Excessive reagent left in the container as well. So do remember this particular point. So limiting reagent is the one which decides everything in the reaction, right? Limiting reagent is going to let you know how many moles of C and D have got formed. Limiting reagent is going to let you know how many moles of excessive reagent are left in the container. All that stuff, limiting reagent is going to let us know. Now the point is how exactly? How limiting reagent is going to let us know all the stuff, right? How exactly? Before that, there's a trick, my dear students, with the help of which you identify the limiting reagent. For example, you have got the reaction. For example, you have got the reaction over here. In this reaction, you need to identify which one is the limiting reagent. How do you exactly identify it? How do you exactly identify it? How do you exactly identify it? My dear students, for example, the stoichiometric coefficient here is N1. Let's say stoichiometric coefficient of A is N1. Let's say stoichiometric coefficient of B is N2 over here, right? How many moles of A I took in the beginning? 10. How many moles of B I took in the beginning? 5. Now, how do you identify the limiting reagent? See, you have got two reactants, A and B, right? You have got two reactants, A and B. How many moles of A do we have in the beginning? 10. How many moles of B we have in the beginning? 5, right? What am I supposed to do? I am supposed to divide the given moles of reactants by their respective stoichiometric coefficients. So 10 divided by N1, 5 divided by N2. I'm supposed to divide the given moles of reactants by their respective stoichiometric coefficients. Now, among these two terms, these are two terms now. Among these two terms, the one which gets the lesser value, for example, if 5 by N2 is less than 10 by N1, if 5 by N2 is less than 10 by N1, then I will be calling this B as the limiting reagent and A automatically I'll be calling as the excessive reagent. So how do I identify the limiting reagent in a reaction? Divide the given moles of the reactants by their respective stoichiometric coefficients. The one which gets the lesser value, that is always going to be the limiting reagent. Is this clear to everyone till now? Is this clear, people? Quickly, you can let me know in the chats. Is every single thing clear, whatever I told you till now? Yes? Perfect. Now, let's try to utilize all these things in the questions so that you'll understand how this concept is used in the questions. Try to understand, people. For example, I'm starting with a basic question. Let's say I've got the question like this. For example, you have got the reaction or let me write the question directly. On starting with 10 moles, each of N2 and H2. On starting with 10 moles each of N2 and H2. Calculate. Number 1. For example, volume of NH3 formed at STP. Let's say this is the first question. Second, moles of excess reagent left. These are the two questions which I have. Okay, these are the two questions which we have. My dear students, first of all, as far as the question is concerned, what reactants do we have? We have got N2, we have got H2. And you know, when N2 and H2 react, they will lead to the formation of what? They lead to the formation of NH3. Okay, perfect. Now, my dear students, if I write at time t is equal to 0, initially we are given with 10 moles each of reactants. So we have got 10 moles of N2 as well as 10 moles of H2 in the container. We have got 10 moles of each of them. So how many moles of NH3 will be there? Initially, there will be 0 moles of NH3 in the container, right? Because the reaction has not started yet. Now, do remember, whenever in a question you are given with the amounts of all the reactants. Whenever in a question you are given with the amounts of all the reactants. Amounts can be in terms of moles, like this. Amounts can be in terms of mass. Amounts can be in terms of volume, particles, etc. Whenever in a question you are given with the amounts of all the reactants, at that point of time, you will use the concept of what? You'll use the concept of limiting reagent, right? And the first step in the limiting reagent concept, what is that? You are supposed to balance the reaction. That is the first step in the limiting reagent concept. Okay, you are supposed to balance the reaction. So try to balance the reaction. This has to be 3 times, this has to be 2 times, and this is 1. Right? I'll balance the reaction. The reaction is balanced now. Okay. Now, after balancing the reaction, I'm supposed to identify which one is the limiting reagent among the 2 reactants. How do I identify the limiting reagent? Divide the given moles by their respective stoichiometry coefficients. The one that gets the lesser value, that has to be the limiting reagent. Yeah. So 10 by 1 is equal to 10. 10 by 3 is equal to 3.33. So which one is getting the lesser value? N2 or H2? Which one is getting the lesser value? N2 or H2? 10 by 1 is 10. 10 by 3 is 3.33. So H2 is getting the lesser value. The one that gets the lesser value, that has to be your limiting reagent. So H2 is my limiting reagent over here. Right? So I identified first of all the limiting reagent. Now, we got to know H2 is the limiting reagent. If H2 is the limiting reagent, that means out of 10 moles of H2, I will be left with 0 moles of H2 because it would have got completely consumed in the reaction. Right? Now, people, I told you already, in the reaction, limiting reagent is the one that decides everything. So let's get to know how many moles of NH3 have got formed when the reaction would have stopped. How many moles of NH3 would have got formed? Who is going to give me the idea about that? Who is going to let me know how many moles of NH3 have got formed? It is the limiting reagent. What I'll be doing, I'll try to relate the stoichiometry of limiting reagent with the stoichiometry of NH3. See, the coefficient here is 3, the coefficient here is 2. Can I say, as per stoichiometry, 3 moles of limiting reagent, as per stoichiometry. Stoichiometry is telling me 3 moles of limiting reagent should give me 2 moles of NH3. Right? Therefore, 1 mole of limiting reagent should give me 2 by 3 moles of NH3. Okay? Therefore, 10 moles of limiting reagent. 10 moles of limiting reagent should have given me 2 by 3 multiplied by 10. Comes out to be 6.66 moles of NH3. So I got to know when the reaction has stopped. 6.66 moles of NH3 has got formed. Okay? Right? Perfect. I got to know 6.66 moles of NH3 have got formed. Now, What is this N2 over here? What is this N2 over here? N2 is the excess reagent. What does that mean? That means out of 10 moles of N2, there will be some moles of N2 still left in the container, right? Because it's the excess reagent. Okay. Now, how do we check exactly? Out of 10 moles of N2, how many moles of N2 are left in the container? Again, limiting reagent is going to give me the idea about that. And how exactly? Try to understand. See guys, what you need to do exactly now, try to relate the stoichiometry of limiting reagent with the stoichiometry of excessive reagent. Understand. See, stoichiometric coefficient here is 3, here it is 1. Can I say stoichiometry is telling us that 3 moles of limiting reagent, reacts with 1 mole of excess reagent, 1 mole of N2. This is something which stoichiometry is telling me. 3 moles of limiting reagent reacts with 1 mole of N2. Therefore, 1 mole limiting reagent reacts with 1 by 3 moles of N2. Correct? If 1 mole limiting reagent reacts with 1 by 3 moles of N2, therefore I can say 10 moles of limiting reagent. Reacts with 1 by 3 multiplied by 10. The value comes out to be 3.33 moles of N2. So try to understand what we calculated. We got to know that 10 moles of limiting reagent. Reacts with 3.33 moles of N2. So 10 moles of limiting reagent have reacted with 3.33 moles of N2. How many moles of N2 we took in the beginning? We took 10 moles of N2 in the beginning. Out of 10 moles of N2, how many moles of N2 are reacting? 3.33 moles are reacting. So how many moles of N2 will be left? It will be 10 minus 3.33. The value comes out to be 6.66 moles of N2 will be left in the container as such at the end of the reaction. Yes? Perfect. So I got to know the moles of NH3 formed. I got to know the moles of N2 that have reacted. I got to know the moles of N2 which are left in the container. But look at the question carefully. I was supposed to calculate volume of NH3 formed at STP. Since I got to know the moles of NH3 formed, now how do you convert moles into volume at STP? Moles multiplied by 22.4, right? So I'll say volume of NH3 which has got formed at STP will be equal to moles of NH3 formed multiplied by 22.4. The value comes out to be in liters, right? Perfect. Second question was calculate the moles of excess reagent left. How many moles of excess reagent are left? It is 6.66. I believe this particular question is clear to everyone. If it is clear, let me know once in the chats. Let me know once in the chats if you got to know how do you use the concept of limiting reagent in the questions. So I'll quickly recap the things. I told you whenever in a reaction we are given with the amounts of all the reactants at that point of time, right? Whenever we are given with the amounts of all the reactants, amounts can be in terms of moles, mass, volume, particles, whatever. At that point, I'll be using the concept of limiting reagent. And in the limiting reagent concept, what am I supposed to do first? I'm supposed to balance the reaction, right? After balancing the reaction, I'm supposed to identify the limiting reagent. How exactly? Given moles of reactants divided by the respective stoichiometric coefficients. The one that gets the lesser value, that's always the limiting reagent. And limiting reagent lately is the one which decides everything in the reaction. I believe I'm clear. Okay? All right. Tell me the answer of this particular question. Tell me the answer of this particular question, guys. Tell me the answer of this particular question. It's again simple. So, as per the question, initially we are starting with 3 moles of NaOH and 4 moles of H2SO4. So initially we are starting with 3 moles of NaOH, 4 moles of H2SO4. What do I have to do? I just have to check which one is the limiting reagent. Yeah. So, in order to check the limiting reagent, my first step is to balance the reaction. The reaction is already balanced. It is given in the balanced format. Now, what am I supposed to do? Divide these given moles by the respective stoichiometric coefficients. The one that gets the lesser value, that is the limiting reagent. So, 3 divided by 2 is 1.5. 4 divided by 1 is 4. So, which one is lesser value among these? 1.5. So, it is NaOH, that is the limiting reagent over here. Yes? Right? Again, a simple and basic question this was. Let's try to see a few more questions so that you can understand things properly. All right. As far as this particular question is concerned, what am I given with? I'm given with a reaction, and the reaction is like this: 6 times LiH plus 8 times BF3. It gives 6 times LiBF4, and with that you have got B2H6. So this is the reaction that's given to me, correct? Try to understand, people. Try to understand. As far as the question is concerned, initially we are starting with 2 moles each of reactants. So we have 2 moles of this and 2 moles of this given. So this will be 0, this will be 0, because the reaction has not started yet. Now if you look carefully, again we are given with the amounts of all the reactants. Again we are given with the amounts of both the reactants. So which concept I'll be using? I'll be using the limiting reagent concept. And in the limiting reagent concept, what am I supposed to do? Right? What is the first thing which I need to do in the limiting reagent concept? I'm supposed to balance the reaction. Right? To understand, the reaction is already balanced, right? Now, identify the limiting reagent. How do you exactly identify the limiting reagent? Given moles divided by the respective stoichiometric coefficients. So, 2 divided by 6 and this 2 divided by 8. Which value comes out to be lesser? 2 by 8 is less than 2 by 6. 2 by 8 is less than 2 by 6. So, your BF3 is your limiting reagent over here, and this automatically becomes your excessive reagent, right? Now, my dear students, if BF3 is the limiting reagent, so it would have got completely consumed. So I would say I'll be left with 0 moles of BF3 finally, right? And since BF3 would have got completely consumed in the reaction, there will be some moles of LiH left. There will be some moles of LiBF4 formed. There would be some moles of B2H6 formed as well, right? And since when this BF3 would have got completely consumed, I would say the reaction would have stopped. I would say the reaction would have stopped. Yes, the reaction would have stopped. Perfect. Now, my dear students, what am I supposed to calculate? Let's try to calculate everything. Whatever things we can calculate, let's try to calculate each and everything. Let's get to know, first of all, how many moles of LiBF4 have got formed at the end of the reaction. Let's get to know that. How many moles of LiBF4 have got formed at the end of the reaction? I told you already, limiting reagent is the one that decides every single thing in a reaction. Yeah, that decides every single thing in the reaction. Try to understand. My dear students, this is my limiting reagent. Relate its stoichiometry with LiBF4. Can I simply say 8 moles of limiting reagent should produce 6 moles of LiBF4. 8 moles of limiting reagent should produce 6 moles of what? 6 moles of LiBF4. Therefore, 1 mole of this limiting reagent should produce what? 6 divided by 8 moles of LiBF4. Right? 1 mole of limiting reagent should produce these many moles of LiBF4. But did I have only 1 mole of limiting reagent? No, I had 2 moles of limiting reagent. So I would say 2 moles of limiting reagent should produce 6 divided by 8 multiplied by 2, which comes out to be 12 divided by 8. 12 divided by 8 is 4342. The value comes out to be 1.5. So you got to know 1.5 moles of LiBF4 would have got formed at the end of the reaction. Okay. Now let's get to know how many moles of B2H6 have got formed at the end of the reaction. Again, who is going to let you know about that? Limiting reagent is going to decide that, right? Now have a look. Stoichiometric coefficient here is 8, here it's 1. Perfect. Now people, you need not to write stuff. You can do it directly. 8 moles of BF3 should give 1 mole of B2H6. 8 moles of BF3 should produce 1 mole of B2H6. 1 mole of BF3 should produce 1 by 8 moles of B2H6. Right? Therefore, 2 moles of BF3 should produce, multiplied by 2, the value comes out to be 1 by 4, or you can say 0.25 moles of B2H6 would have been produced at the end of the reaction. Yes, simple. Now, what is this LiH over here? LiH is our excessive reagent. If it is excessive reagent, that means out of 2 moles of LiH, there will be some moles of LiH still left in the container. Now, who is going to let us know about that? Again, limiting reagent is going to let us know how many moles of LiH will be left in the container at the end of the reaction. How exactly? Try to understand. Hey guys, now do one thing. Relate the stoichiometry of limiting reagent with the stoichiometry of what? LH. I can say something like this. I can say 8 mole limiting reagent. I can say 8 mole limiting reagent. As per stoichiometry, 8 mole limiting reagent reacts with 6 moles of LiH. 8 moles of limiting reagent reacts with 6 moles of LiH. Therefore, I can say 1 mole limiting reagent reacts with 6 by 8 moles of LiH. Or I can say 2 moles of limiting reagent. 2 moles of limiting reagent would have reacted with 6 by 8 multiplied by 2. The value comes out to be 1.5 moles of LiH. So you got to know exactly 2 moles of your limiting reagent. 2 moles of your limiting reagent would have reacted with 1.5 moles of LiH. How many moles of LiH I took in the beginning? I took 2 moles of LiH, out of which how many are reacting? 1.5 moles are reacting. So 2 minus 1.5. 2 minus 1.5 comes out to be 0.5. So I'll say 0.5 moles of LiH will be still left in the container as such in the unreacted form. If I'm clear, let me know once in the chats quickly. I believe you should be able to solve all these questions on your own now. Right, people? All clear? All clear, all clear? Quickly in the chats. Perfect. Let's try to solve a few more questions so that every single thing will be absolutely clear to you. Look at this question, guys. Look at this question. As far as the question is concerned, we are given the reaction. The reaction is something like this. 3 times BaCl2 plus 2 times Na3PO4. Right? It gives Ba3PO4 whole twice plus 6 times NaCl. Plus 6 times NaCl. This is my reaction. This is my reaction, guys. Yes, PDF I'll be sharing on my Telegram, right? Which is WASSIM BHAT chemistry-official. Yeah? Okay. Perfect. So my dear students, look at this particular question. The question is saying on starting with 10 moles each of reactants. So we are starting with 10 moles each of reactants. I'm taking 10 moles of BaCl2. At the same time, I'm taking 10 moles of this species as well. I'm taking 10 moles each of reactants. So initially at time t is equal to 0, we have got 10 moles each of reactants. Since I'm saying at time t is equal to 0, what does that mean? That means the reaction has not started yet. That means the reaction has not started yet. So moles of this as well as moles of this will be 0 initially, right? Now, if you look carefully, am I given with the amounts of all the reactants? Yes, I'm given with the amounts of all the reactants. Right? Yes, I'm given with the amounts of all the reactants. So which concept I'll be using? Again, limiting reagent concept. What is the first thing? I'm supposed to balance the reaction. And the reaction is already balanced. The reaction is already balanced. Now, after balancing the reaction, I'm supposed to identify the limiting reagent. How exactly? Given moles divided by respect to stoichiometric coefficients. The one that gets the lesser value, that has to be your limiting reagent. Right? So 10 divided by 3. 10 by 3 is equal to 3.33. 10 by 2 is equal to 5. So which one is getting the lesser value? BaCl2. So BaCl2 is my limiting reagent. Okay. If BaCl2 is the limiting reagent, I would say it would have got completely consumed in the reaction. So I would say out of 10 moles of BaCl2, there will be 0 moles of BaCl2 left in the container at the end. And finally, the reaction would have stopped. What am I supposed to calculate? I'm just supposed to calculate the moles of barium phosphate formed. The moles of this Ba3PO4. How many moles of Ba3PO4 would have got formed at the end of the reaction? Who gives me the information about that? It is the limiting reagent which gives me the information about every single thing in the reaction, right? So what I'm going to do over here, I will be trying to relate the stoichiometry of limiting reagent with this Ba3PO4 whole twice, right? Now, my dear students, look carefully. Stoichiometry is telling us 3 moles of BaCl2. Stoichiometry is telling us that 3 moles of BaCl2 gives 1 mole of barium phosphate. Gives 1 mole of barium phosphate. 3 moles of BaCl2 gives 1 mole of barium phosphate. Therefore, Therefore, 1 mole BaCl2 gives us what? It gives us 1 by 3 moles of barium phosphate. Correct? 1 mole of BaCl2 will give us 1 by 3 moles of barium phosphate. How many moles of BaCl2 do we have? We have 10 moles of BaCl2. Therefore, I would say 10 moles of BaCl2 would be giving us what? It would be giving us 1 by 3 multiplied by 10. The value comes out to be 3.33 moles of barium phosphate. Right? So what did I calculate over here? I would say these are the moles of barium phosphate which have got formed at the end of the reaction. Isn't this something which I was supposed to calculate? Yes. Right? Now you can calculate all the other things as well. If I ask you, calculate the moles of NaCl formed. How do you calculate the moles of NaCl formed? Simple. Start with the limiting region again. 3 moles are giving us 6 moles. So 1 mole will give me 6 by 3. That means 2 moles. Therefore, 10 moles will give me 2 into 10. That means 20 moles. So 20 moles of NaCl would have got formed at the end of the reaction. Now, it is not necessary that they'll ask you about the moles only. They can ask you about the mass. Now, you know how do you convert moles into mass? Moles multiplied by molar mass of the substance gives us the mass, right? Similarly, if I ask you, what is the mass of NaCl formed? You got to know the moles. Multiply that with the molar mass of NaCl. Get the mass of NaCl formed, right? Anything can be asked, people. I believe this is clear. I believe this is clear to everyone. Okay? I believe this is perfectly clear to everyone. All right, for example, I'm writing one simple question like this. On starting with 10 grams of H2 and 128 grams of O2. Calculate. Number 1. The mass of water formed. The mass of water formed. Number 2. The mass of excessive reagent left. Mass of excessive reagent left, right? You can solve this sort of equation quickly now, I believe. See, first of all, H2 and O2 is going to react. Okay, and you must be knowing when H2 reacts with O2, it leads to the formation of what? It leads to the formation of H2O. Perfect. Now, my dear students, think carefully. Am I given with the moles of H2 and O2? I'm not given with the moles of H2 and O2. I'm given with their masses. I'm given with their masses. But do we start with masses or we start with moles? We start with moles, right? We start with moles. Now, what do I need to do first? I'm supposed to convert these given quantities into moles. 10 grams of H2 means 5 moles of H2, right? Given mass divided by its molar mass, that's 2. 10 by 2 is 5, correct? Given mass divided by its molar mass, that is 32. So 128 divided by 32, that's 4. So I believe initially we are starting with 5 moles of H2 and 4 moles of O2. And this will be 0 initially because the reaction has not started yet. Now people tell me one thing. Am I given with the amounts of all the reactants? Yes. Which concept? Limiting region concept. In the limiting region concept, what am I supposed to do? I'm supposed to balance the reaction first. So try to balance the reaction. This has to be 2 times. This has to be 2 times. The reaction is balanced. After balancing the reaction, what are you supposed to do? Identify the limiting reagent. How exactly you'll be identifying the limiting reagent? Given moles by their respective stoichiometric coefficient. Given moles by their respective stoichiometric coefficients. The one that gets the lesser value, that's the limiting reagent. 5 divided by 2, that is 2.5. 4 divided by 1, that's 4. So H2 is getting the lesser value, so I would say this H2 is my limiting reagent here. If H2 is the limiting reagent, it would have got completely consumed and I'll be left with 0 moles of H2. I'll be left with 0 moles of H2, right? Now, when H2 would have got consumed, I would say reaction would have stopped. Now, people, you know, in the reaction, every single thing is decided by what? Every single thing is decided by the limiting reagent, right? Let's try to get one by one the things. Have a look. First of all, let's get to know how many moles of water have got formed. Let's get to know how many moles of water have got formed. Okay? Who's going to decide that? Limiting reagent. Just try to relate the stoichiometry of limiting reagent with the stoichiometry of water. Simple, right? So stoichiometry is telling me that 2 moles of limiting reagent gives me 2 moles of water. 2 moles of limiting reagent should give us 2 moles of water, right? Therefore, I can say 1 mole of limiting reagent should give us 1 mole of water. How many moles of limiting reagent we had? 5 moles. So 5 moles of limiting reagent should give us 5 moles of water. So I got to know at the end of the reaction what you'll observe 5 moles of water would have got formed. 5 moles of water would have got formed at the end of the reaction, right? Perfect. But as per the question, was I supposed to calculate moles of water formed? No, I was supposed to calculate mass of water formed. My dear students, you know, how do you convert moles into mass? I'll say mass of water formed will be equal to moles of water formed multiplied by molar mass of water. That's 18 grams, 5, 8, 40. So it will be 90 grams. So I got to know 90 grams of water has got formed at the end of the reaction. 90 grams of water has got formed at the end of the reaction. Yeah. Now, what is the second thing? Calculate the mass of excessive reagent left. How many moles of excessive reagent we had? 4. Now, out of these 4 moles, there will be some moles of excessive reagent still left in the container. So, first of all, let's get to know how many moles of excessive reagent are left in the container. Who is going to let me know about that? Again, it's going to be the limiting reagent that's going to let me know about that as well. I don't understand. See guys, this is my limiting reagent. Try to relate the stoichiometry of limiting reagent with the stoichiometry of this excess reagent. Stoichiometry is telling me that 2 moles of limiting reagent reacts with 2 moles of limiting reagent reacts with 1 mole of O2, right? 1 mole of O2. Therefore, 1 mole of limiting reagent should react with 1 by 2 moles of O2. Correct? I would say 5 moles of limiting reagent. 5 moles of limiting reagent should react with 1 by 2 multiplied by 5. That means 2.5 moles of O2. So I got to know 5 moles of your limiting reagent are reacting with 2.5 moles of O2. So 5 moles of limiting reagent are actually reacting with 2.5 moles of O2. How many moles of O2 we had? 4. Out of 4 moles of O2, how many moles of O2 are reacting? 2.5. So how many will be left? So 4 minus 2.5. The value comes out to be 1.5. So 1.5 moles of O2 will be left in the container at the end. These are the moles of O2 left. But as per the question, am I supposed to calculate moles of O2? No, I'm supposed to calculate mass of O2 left, right? So I'll say mass of O2 left in the container will be equal to moles of O2 left, 1.5 multiplied by molar mass of O2, right? Multiplied by molar mass of O2. And this value, I believe it comes out to be 48 grams, right? So 48 grams of O2 will be left in the container at the end of the reaction. If this is clear, let me know once in the chats. Yes? Is it clear? Is it clear to everyone? Can you let me know quickly? Let me know, people, quickly in the chats if this is super clear to everyone. All right, you can do one more question. One simple question you can do. Let me see if you can solve that or not. The question is, for example, on starting with 112 liters of H2 and 224 liters of Cl2 at STP. And by the way, these are the gases, right? H2 gas, Cl2 gas at STP. Calculate. Number 1. So for example, the first question is telling you that identify the limiting reagent. This is your first question. Identify the limiting reagent. Second question. Calculate the volume of HCl gas formed at STP. Second question. Third question. Calculate the volume of calculate the volume of excessive reagent left at what? At STP. Can you solve this question on your own? Can you solve this question on your own? It's simple. You should be in a position to solve this. You should be able to solve this. So first of all, my dear students, you should first of all know the reaction, right? What's going to be my reaction? As per the question, your H2 gas is reacting with Cl2 gas. It will lead to the formation of HCl gas, right? This is the reaction, which I already wrote in the balanced form. This is the reaction which I already wrote in the balanced form. Now at time t is equal to 0, what am I given with? I'm given with the volume of the reactants. I'm given with the volume of the reactant. But do we start with the volume? We do not start with the volume. We start with the moles. So convert these given quantities into moles first. Yeah? Convert these given quantities into moles first. So given volume divided by 22.4, right? Given volume divided by 22.4. How much that comes out be? So how many moles of H2 we have? How many moles of H2 we have? 5 moles, right? Given volume of H2 in liters divided by 22.4, that comes out be 5. Similarly, how many moles of Cl2 do we have? Given volume divided by 22.4, the value comes out be 10. So we are starting with this particular thing. So this will be 0 in the beginning. Now, which one is the limiting reagent among the two? Divide these given moles of reactants by their respective stoichiometric coefficient. The one that gets the lesser value, that's always the limiting reagent. So 5 by 1 is 5, 10 by 1 is 10. So which one is limiting? H2 is limiting here. If H2 is limiting, that means these 5 moles would have got completely consumed. I'll be left with 0 moles. And eventually, the reaction would have stopped. Eventually, the reaction would have stopped, right? Now, we will try to understand. Everything in the reaction is decided by whom? Limiting reagent. How exactly? Let's have a look. I'll say 1 mole of limiting reagent gives 2 moles of HCl. If 1 mole limiting reagent gives 2 moles of HCl, 5 moles of limiting reagent would have given 10 moles of HCl. So I would got to know that 10 moles of HCl have got formed. 10 moles of HCl have got formed, right, at the end. Now, 1 mole limiting reagent reacts with 1 mole of Cl2. 5 moles of limiting reagent reacts with 5 moles of Cl2. I had taken 10. Out of 10, 5 are reacting. So I'll be left with 5 moles. 10 minus 5 is 5. So 5 moles of Cl2 will be left in the container as such. Yeah? But was I supposed to calculate moles or I was supposed to calculate volume? First of all, I was supposed to calculate volume of HCl formed, which will be equal moles of HCl multiplied by 22.4. The value comes out to be 224 liters. So 224 liters of HCl would have got formed at the end, right? Similarly, how many moles of, what is the volume of excess reagent left? We got to know the moles of excess reagent left. Moles multiplied by 22.4, that gives me the volume. I would say volume of excessive reagent, volume of Cl2, which is left in the container at the end, is equal to moles multiplied by 22.4. The value comes out to be how much? 112 liters, right? This is the volume of Cl2 which is left in the container. So these sort of questions, I believe, can be asked from the limiting reagent concept, and I'm pretty much sure you can easily solve these sort of questions on your own from now onwards. If it is clear, then I'll move on to one more concept. Yeah? Quickly. Let me know in the chats if all these things are clear till now. Let me know in the chats, then I'll move on to one more concept. Quickly. And questions are frequently asked from that concept too. Let me know once in the chats. All clear? I would want every one of you to let me know in the chats if all these things are clear. I feel everything is clear. Okay. So let's move on to one more concept now, that is percentage yield. This is again frequently asked. Okay. Percentage yield. So what this percentage yield exactly is all about and what kind of questions are asked? There are like 4 to 5 different types of questions that can be asked from percentage yield, right? Okay. there are 4 to 5 different types of questions that can be asked from percentage yield. So first of all, let's get to know how do we calculate percentage yield and what kind of questions are frequently asked from this percentage yield concept. See, my dear students, let me first of all write the formula with the help of which we calculate the percentage yield. Okay, let me write the formula. How do we exactly write the formula? The formula is percentage yield. Percentage yield is always equal to experimental or the actual amount, divided by expected or the theoretical amount multiplied by 100. This is the formula with the help of which we can calculate the percentage yield of the reaction. Actual amount divided by theoretical amount, or you can say experimental amount divided by expected amount multiplied by 100. That gives me the yield of the reaction. Now, so what is yield? What exactly it is? Let me give you one simple analogy to understand the yield. For example, I'm asking you, how many marks do you expect in NEET? How many marks do you expect in NEET? You're telling me 700 marks. This is your expected mark. This is your expected score. Right? I'm asking you a question. How many marks do you expect in the NEET? You told me 700. Right? This is your expectation. When you wrote NEET, for example, you got 680. This is actual. This is actual score. This is experimental score. If I ask you to calculate your yield, what do you say? You'll say your experimental or actual score is 680. Your expected was 700 multiplied by 100. This is going to be giving you your yield. Okay? I hope you got the idea of what this yield is all about. Yield, or you can call it as efficiency as well. This is going to give you your efficiency. Yeah? Right? Now, let's try to introduce this concept in the reactions so that you'll get to know how exactly the questions are asked from this percentage yield. Okay? One thing I'm going to tell you. Expected amount, or you call it as the theoretical amount, we always calculate it with the help of stoichiometry. Stoichiometry is going to give us always the expected amount. What is stoichiometry? Stoichiometry, whatever we have been doing till now. Limiting, reagent, stoichiometry, all of this we do on pen paper, right? All of this we do on pen paper. I tell you 3 moles should give 2 moles, 1 mole should give this, 5 moles should give this. All that thing happens in pen paper only, right? Perfect. So that's all theoretical. So whatever things we get from stoichiometry, that's all theoretical. That's always expected. That's something which we expect in the reaction. In reality, things can be different as well. What exactly I'm trying to say? Let's have a look. What exactly am I trying to say? Look at the question. You'll understand everything. The question is saying that on heating 40 grams of calcium carbonate, as per the question, they are telling you that on heating 40 grams of calcium carbonate, it was observed that 20 grams of calcium oxide was produced. This is something which is given to me in the question. In the question, they are telling you that when you heat up 40 grams of calcium carbonate, 20 grams of calcium oxide is produced. So this is the data which is given to me as per the question. So this would be experimentally verified data, right? This would be experimentally verified data. It is mentioned in the question that on heating 40 grams of calcium carbonate, 20 grams of calcium oxide is produced. So this is something which would have been observed in the lab. When you actually would be heating up 40 grams of calcium carbonate, 20 grams of calcium oxide was produced. So this is something which is given to me as per the question. So this is my experimentally verified data. And it's mentioned that when you heat up 40 grams of calcium carbonate, 20 grams of calcium oxide is produced, right? So this is experimentally verified. So I'm calling this particular data as the experimental or actual amount. This is my experimental amount. In order to calculate the yield, how many amounts do I need? I need two amounts, experimental and expected. Experimental I got. Now, I would want to calculate the expected amount. How would I be calculating the expected amount? I would be calculating the expected amount with the help of what? With the help of stoichiometry. Now, stoichiometry is going to give me the expected amount. How exactly? Balance the reaction first. It's already balanced. Now, tell me one thing. What is the molar mass of calcium carbonate? Molar mass of calcium carbonate is 100 grams. That means mass of 1 mole of calcium carbonate is 100 grams. Mass of 1 mole of calcium carbonate is 100 grams. And over here, I exactly have 1 mole of calcium carbonate. So instead of this 1 mole of calcium carbonate, I can write 100 grams of calcium carbonate. 100 grams of calcium carbonate. What is the molar mass of calcium oxide? It will be 64 grams. That means the mass of 1 mole of calcium oxide is 64 grams. So basically, see what stoichiometry is telling me. Stoichiometry is telling me that 100 gram calcium carbonate upon heating should produce 64 grams of calcium oxide. This is something which stoichiometry is telling me, that 100 grams of calcium carbonate upon heating should produce 64 grams of calcium oxide. I'm using the term should, right? Therefore, 1 gram calcium carbonate upon heating should produce how much? 64 divided by 100 grams of calcium oxide. Okay, so 1 gram of calcium carbonate should produce these many grams of calcium oxide. But did we have 1 gram of calcium carbonate? No, we have 40 grams of calcium carbonate. So I would say from stoichiometry, I can say 40 grams of calcium carbonate upon heating should produce how much? 64 divided by 100 multiplied by 40 grams of just a second, is it 64 here? 40 plus 16, sorry, it's 56. This is 56 here, right? Okay, just modify this. Just modify this. Okay, multiplied by 40 grams of calcium oxide. I hope it's clear till now. Yes, 56. So I got to know one thing. 40 from stoichiometry. Stoichiometry told us that, it gave us the information that 40 grams of calcium carbonate upon heating should produce these many grams of calcium oxide. Should produce these many grams of calcium oxide. And after solving it comes out to be 22.4 grams. So try to understand what did we calculate. We got to know with the help of stoichiometry. With the help of stoichiometry, we got to know that 40 grams of calcium carbonate upon heating should produce these many grams of calcium oxide. So this is something which I was expecting to get formed, right? This is something which I was expecting to get formed. I was expecting that with the help of stoichiometry, I was expecting that 40 gram calcium carbonate upon heating should produce 22.4 grams of calcium oxide. So this is something which I was expecting to get formed. So this is my expected amount, which I got to know with the help of stoichiometry. What is the experimental amount? In reality, 20 grams of calcium oxide is produced. How much should have got produced? 22.4, right? So I can directly calculate the yield. Percentage yield is equal. Experimental amount divided by expected amount multiplied by 100. When you solve this, you get the value exactly as 89%. So the percentage yield of the reaction, the yield of the reaction is nothing but 89%. Yeah? The yield of the reaction is 89%. My dear students, understand one thing. If the yield of the reaction was 100%, if the yield of the reaction was 100%, at that point of time, whatever amount of calcium oxide you would have expected, same amount would have got formed in reality as well. Understand the words which I'm telling. Understand the words which I'm telling. If the yield of the reaction was 100%, whatever amount of calcium oxide was expected to get formed with the help of stoichiometry, in reality also, same amount of calcium oxide would have got formed. But when? When the yield of the reaction was what? If the yield of the reaction was 100%. Okay? Over here, the yield of the reaction is 89%. That means whatever amount you expected, not entirely this amount was formed in reality. I would say 89% of this amount, 89% of this amount was formed in reality. If you do one thing, if you calculate 89% of the expected amount, 89% of this amount, when you calculate it, it will come out to be 20 only. It will come out to be 20 only. Okay? Right? I believe this is clear. I believe this is clear. All right. Let's try to solve a few more questions so that it will be properly clear to you. Look at this question, guys. Look at this question. Similar type of question. As far as the question is concerned, we are given the reaction. Benzene plus HNO3 gives nitrobenzene plus water. Now, first of all, let me write the reaction again. C6H6 plus HNO3. What does it produce? It produces C6H5NO2 plus H2O. This is the reaction. This is the reaction. Now, as far as the question is concerned, the question is saying that as far as the question, 15.6 grams of benzene, right, when mixed with HNO3, produces 18 grams of nitrobenzene. This is something which is given to me as per the question. So this would be definitely experimentally verified, right? It would be experimentally verified that 15.6 grams of benzene on reaction with nitric acid would be giving 18 grams of nitrobenzene. This is something which is experimentally verified. So I'll be calling this 18 grams over here as what? This is my actual amount, this is my experimental amount. Because it is given to me as per the question. In the question, whatever data is given, that is your actual amount, which is experimentally verified. Now, what do I need? I got the experimental amount. What do I need now? I need the expected amount. Expected amount I get from where? From stoichiometry. Yeah? Now we use the stoichiometry. Understand. The reaction, first of all, is balanced. What is the mass of 1 mole of benzene? 78 grams. 78 grams. What is the mass of 1 mole of nitrobenzene? When you calculate it, it will be 123 grams of nitrobenzene, which is basically its molar mass. Molar mass of nitrobenzene is 123 grams. That means the mass of 1 mole of nitrobenzene is 123 grams. Now, people, tell me one thing. Can I say, as far as the question is concerned, the stoichiometry is telling me that 78 grams of benzene should produce 123 grams of nitrobenzene. Therefore, 1 gram benzene should produce how much? 123 divided by 78 grams of nitrobenzene. Yes. Therefore, 15.6 grams of benzene. 15.6 grams of benzene should produce these many grams of nitrobenzene. When you solve this, this value comes out to be 24 grams. So I got to know with the help of stoichiometry, I got to know that 24 grams of nitrobenzene should have got produced from 15.6 grams of benzene. So from 15.6 grams of benzene, how much nitrobenzene should have got produced? Stoichiometry is telling you that, right? So 24 grams. So this is something which I was expecting to get formed. So this is my expected amount. You got both the amounts, experimental as well as expected. So you can exactly calculate the yield of the reaction. Percentage yield is equal to experimental amount, actual amount divided by expected multiplied by 100. All this, get the yield of the reaction. As simple as that. Yeah. I hope this is clear. I hope this is clear. Perfect. All right. One more question I'm giving you. It is of the similar type. I believe you can solve this question on your own. Similar type of question. It can be your homework question, right? It is a similar type of question. You can solve this question on your own. So I'm not solving this one over here. Let me move on to one more question. Look at the reaction carefully and see what exactly are we supposed to calculate. See, guys, on heating 150 grams of calcium carbonate, what mass of calcium oxide would be formed? On heating 150 grams of calcium carbonate, what mass of calcium oxide would be formed if the yield of the reaction is 75%? One thing which we already know, if the yield of the reaction was 100%, whatever amount of calcium oxide was supposed to get formed, same amount of calcium oxide would have got formed in reality as well. But the yield of the reaction is less than 100, right? Okay, so how exactly I'm going to solve this? Understand. See guys, first of all, the reaction is balanced. What is the mass of 1 mole of calcium carbonate? That means molar mass. It's 100 grams. So I can write 100 grams of calcium carbonate upon heating. What is the mass of 1 mole of calcium oxide? 56 grams. Molar mass of calcium oxide. Okay. Can I say, as per stoichiometry, 100 grams of calcium carbonate upon heating should produce 56 grams of calcium oxide? Yes. 100 grams of calcium carbonate upon heating should produce 56 grams of calcium oxide. Therefore, 1 gram of calcium carbonate upon heating should produce 56 divided by 100 grams of calcium oxide. Therefore, 150 grams of calcium carbonate upon heating should produce 56 divided by 100 multiplied by 150 grams of calcium oxide. When you solve this value, I believe it comes out to be, how much this value comes out to be? Can you check it out? I think 84 grams. So what is this 84 grams? This is the mass of calcium oxide which should get formed as per stoichiometry. Right? This is the mass of calcium oxide which should get formed as per stoichiometry. But in reality, this much amount of calcium oxide won't be getting formed. This much amount of calcium oxide would have got formed in reality if the yield of the reaction was 100%. But look at the yield. The yield is 75%. So that means whatever amount of calcium oxide you expected to get formed, I would say 75% of the expected amount, will be getting formed in the reality. So I would say the actual amount of calcium oxide which will be getting formed will be equal to 75% of what? 75% of the expected amount. When you solve this, the value comes out to be 63 grams. So 63 grams of calcium oxide would be getting formed in reality. I believe this is clear to everyone. Okay. Now guys, this sort of a question, whenever it's asked, this sort of a question, you can remember it in the form of trick as well. See, I was given with the amount of reactant. And I was supposed to calculate the amount of product. Right? I was given with the amount of reactant. And I was supposed to calculate the amount of product. Right? From reactant to product. I was given with the amount of reactant. I was supposed to calculate the amount of product. So what I did first of all, I calculated the expected amount first. I calculated the expected amount of product. with the help of stoichiometry. And later on, multiplied the expected amount with the percentage yield. That's what I did. Look carefully. I calculated the expected amount first and later on multiplied the expected amount with the percentage yield. Right? So, when reactant is given to us, product we are supposed to calculate. What am I supposed to do first? Calculate the expected amount and then multiply that with the percentage yield. Right? Multiply that with the percentage yield. Now guys, if the question is given in the reverse form, imagine that in the question the product is given and you are supposed to calculate reactant. Imagine that product is given. Like in this question, reactant was given, product was to be calculated. For example, you will be having a question in which product is given, reactant is to be calculated. So first of all, what you will be doing, you will be calculating the expected amount of reactant. And later on, whatever expected amount of reactant you got, later on divide that with the percentage yield. So you can remember it directly in the short form, right? Or let me write it over here. From reactant to product, multiply with percentage yield. From product to reactant, divide with percentage yield. That's all. Okay? Am I clear with this? Am I clear with this, people? Am I clear with this? Do remember it. Do remember it. Let's try to solve one more question. Look at this question. Look at this question carefully, guys. I hope that question is clear to you, yeah? Or should I give you one question for this as well? For this as well. Should I give you one question for this? Should I give you one question for this? Let me give you one question so that it will be properly clear to you, okay? All right. Calculate the mass of calcium carbonate required to produce, I'm giving you the same question but in reverse form. Calculate the mass of calcium carbonate required to produce 63 grams of calcium oxide if the yield of the reaction is 75%. Okay, if the yield of the reaction is 75%. See, guys. First of all, you know the reaction, your calcium carbonate. Upon heating, it gives calcium oxide plus carbon dioxide. Now, as per the question, how many grams of calcium oxide should be getting formed? 63 grams of calcium oxide should have got formed. We need to make 63 grams of calcium oxide. Now, in order to make 63 grams of calcium oxide, how many grams of calcium oxide are required? How many grams of calcium carbonate are required if the yield of the reaction is 75%? If the yield of the reaction is 75%. So whose data I'm given with? I'm given with the data for the product. I'm supposed to get the data of reactant. Product is given. Reactant is to be calculated. What do I need to do first? I'll be calculating the expected amount of reactant first. Right? Right, people? I'll be first of all calculating the expected amount of calcium carbonate. And later on, I'll be dividing that with the percentage yield. Something which I told you. Now try to understand. What is the mass of 1 mole of calcium oxide? It is 56 grams. So I'll say 56 grams of calcium oxide. 56 grams of calcium oxide is produced from mass of 1 mole of calcium carbonate. That's 100 grams. So I can say stoichiometry is telling us that 56 grams of calcium oxide is produced from 100 grams of 56 grams of calcium oxide should be produced from 100 grams of calcium carbonate. So 1 gram of calcium oxide should be produced from 100 divided by 56 grams of calcium carbonate. Therefore, 63 grams of calcium oxide should be produced from 100 divided by 56 multiplied by 63 grams of calcium carbonate. So, what is this? This is the expected amount of calcium carbonate, which I got with the help of stoichiometry. I got the expected. But what do I need? I need the actual one. How do I calculate the actual amount of calcium carbonate which is required? I got the expected. What do you need to do? Expected divided by percentage yield. Expected is 63 multiplied by 100 divided by 56 all divided by what? Percentage yield, which is 0.75. When you calculate this, the value comes out to be 150. Right? The value comes out to be 150 grams. Am I clear? So I just showed you the same thing, what I told you right now. Okay? If reactant is given, product is to be calculated, multiply with percentage yield. If product is given, reactant is to be calculated, then divide with percentage. That's all. That's all, people. Yes? Let me know once the chats if all these things are clear. Perfectly done. It is a previous question only, but in the reverse format. All right, let's try to solve one more question. Look at this question, guys. The question is 0.4 moles of PCl5 combines with 1.8 moles of water. If 65.7 grams of HCl is formed, calculate the yield of the reaction. See how this question is to be solved. As per the question, you are making PCl5 to react with water. It will lead to the formation of H3PO4, and with that you'll be getting HCl. With that you'll be getting HCl, right? Check if the reaction is balanced or not. Check if the reaction is balanced or not. The reaction is balanced. The reaction is balanced. Now try to understand what exactly are we given with and how we are going to solve this. As far as the question is concerned, the question is saying that on starting with 0.4 moles of PCl5 and 1.8 moles of water. As far as the question, 65.7 grams of HCl is produced. So this is the data that's given to me as per the question. It's experimentally verified data. It's mentioned in the question that when 0.4 moles of PCl5 combines with 1.8 moles of water, it's mentioned clearly in the question that 65.7 grams of HCl has got formed. So this is my actual amount, this is my experimental amount. This is my experimental amount. Now what do I need? I need the expected amount. How do I calculate the expected amount? With the help of stoichiometry. Now, what exactly I'll be using? I'm given with the amounts of both the reactants. So I'll be using the limiting reagent concept. With the help of limiting reagent concept, I'll get to know how many grams of HCl should get formed. Right? And then we'll be done. Reaction is already balanced. Now, which one is limiting among the two? 0.4 by 1 is equal to 0.40. 1.8 divided by 4 is equal to 0.45. So which one is lesser? This value is lesser. So PCl5 is your limiting reagent. This is my limiting reagent. If this is my limiting reagent, I'll be left with nothing. 0 moles of PCl will be getting formed. Now this PCl5 is going to decide how much HCl should have got formed. Now try to understand. 1 mole PCl should produce 5 mole HCl. 1 mole PCl should produce 5 mole HCl. 0.4 mole PCl5 should produce 5 multiplied by 0.4. The value comes out to be 2 moles of HCl. So 2 moles of HCl should have got formed as per stoichiometry, as per limiting reagent. 2 moles of HCl should have got formed. So how many grams of HCl should have got formed? It will be 2 multiplied by its molar mass, right? What is the mass of HCl that should have got formed? It will be equal to moles of HCl multiplied by molar mass of HCl. Molar mass is 36.5. The value will be 73 grams. So I would say stoichiometry is telling us, limiting reagent is telling us that 73 grams of HCl should have got formed. So this is my expected amount. This is my expected amount. But in reality, how much is getting formed? 65.7. This is my expected amount. Okay, this is my actual amount. So if I need to calculate the percentage yield, it will be equal to experimental amount divided by expected amount multiplied by 100. Right? You're done. You are done. Am I clear? Am I clear, people? Am I clear to everyone? Quickly in the chats. I hope these sort of questions you will be able to solve easily from now onwards. I believe that. One more type of question that can be asked from the percentage yield. Have a look, people. For example, I'm writing a question like this. 4 times NH3 plus 5 times O2. This is 4 times NO plus 6 times water. Let's say the yield of the reaction is 70%. Now, 2 times NO plus O2. It gives 2 times NO2. Let's say the yield of the reaction is 50%. Now, 3 times NO2 plus water gives NO plus 2 times HNO3. Let's say the yield of this reaction is 30%. Now, the question is telling you that calculate the mass of HNO3 formed. Calculate the mass of HNO3 formed on starting with 224 liters of NH3 gas at STP. Let's say this is the question. Will you be able to solve this question on your own? Will you be able to solve this question on your own? See exactly, people, how this sort of equation is solved. See, first of all, these are the sequential reactions. If you remember, in the last session, we have discussed sequential reactions. In the first reaction, NO is getting formed. Whatever NO will be getting formed in the first reaction, same amount of NO would be consumed here, right? In the second reaction, NO2 is getting formed. Whatever NO2 will be getting formed here, right? That entire NO2 would be consumed here. And at the end, what is formed? HNO3 is formed. It is just how mentioned some extra things here. What are those extra things? I've mentioned these percentage yields over here, right? Now, what do you need to do? Try to understand, guys, what I'm going to say. See, as far as the question is concerned, we are given with 224 liters of NH3 at STP. What is our first step always in the mole method? Convert the given quantity to moles. So how many moles of NH3 do we have? Given volume of NH3 in grams divided by 22.4. So we are starting with 10 moles of NH3. As per the question, we are starting with 10 moles of NH3. Okay, we are starting with 10 moles of NH3. Now, stoichiometry is telling me that 4 mole NH3 should produce 4 mole NO. I'm not writing anything. 4 mole NH3 should produce 4 mole NO. So 1 mole NH3 should produce 1 mole NO. 10 moles of NH3 should produce 10 moles of NO. So 10 moles of NO should get produced. 10 moles of NO should get produced. But what is the yield of the reaction? 70%. So in reality, 10 moles of NO won't be getting produced. Only 70% of 10. 70% of 10 means 70% of 10 means 7 moles. So 7 moles of NO would be getting produced in reality in the first reaction. Right? Now, whatever moles of NO have got produced in the first reaction, all those will be consumed here. How exactly? Try to understand. 2 moles of NO gives us 2 moles of NO2. So 1 mole of NO gives us 1 mole of NO2. 7 moles of NO will give us, 7 moles of NO should give us, it should give us 7 moles of NO2. It should give us 7 moles of NO2. But in reality, will 7 moles of NO2 get formed? No. 50% of 7 moles. 50% of 7 means 50 by 100 into 7. That means in reality, only 3.5 moles of NO2 would get formed. Okay? Because the yield of the reaction is 50%. Now, whatever NO2 has got formed in the second reaction, all that would have got consumed in the third reaction, right? Now, see, 3 moles are giving us 2 moles. As per the stoichiometry, I can say 3 mole NO2 should produce 2 mole HNO3, right? Therefore, 1 mole NO2 should produce 2 by 3 moles of HNO3. So 3.5 moles of NO2. 3.5 moles of NO2 should produce 2 by 3 multiplied by 3.5. So this is 7 by 3. So 7 by 3 moles of HNO3 should get produced. But the yield of the reaction is 30%. So I won't say, I will not say that, see, these are the moles of HNO3 which should get produced. But in reality, only 30% of this amount will be getting formed. So how many actual moles of HNO3 will be getting formed? 30%. 30 divided by 100 of 7 by 3, which comes out to be 3, 1, 3, 10, 10, 1, 10, 10. So it will be 0.7. So 0.7 moles of HNO3 would be getting formed in reality. So in reality, 0.7 moles of HNO3 would be getting formed. Right? In reality, 0.7 moles of, right? 0.7 moles of HNO3 would be getting formed. So you got to know the actual moles of HNO3 which are getting formed at the end of the reaction. But were you supposed to calculate the moles of HNO3 or mass? We were supposed to calculate mass. So what would be the actual mass of HNO3 that would be getting formed? Moles multiplied by its mole mass, right? So all this, the value comes out in grams. So this is the actual mass of HNO3 which is getting formed at the end. Yes? Perfect, people? Perfect, perfect, perfect. Do you know one direct method of solving this question? Do you want to know a direct method? Do you want to know one more method of solving this question? See, understand what I'm going to do. We are given the amount of reactant. We are supposed to calculate the amount of product. Reactant is given, product is to be calculated. So I'll be calculating the expected amount of product first, then multiply that with the percentage yield at the end. Something which I told you before. See, understand. Just forget the fact that you are given the percentage yields. Forget it. Forget it. Do one thing. 4 moles are giving us, 4 moles should give us 4 moles. 1 mole should give us 1 mole. So 10 moles should give us 10 moles. So 10 moles of NO should get formed technically. 10 moles of NO should get formed, right? And whatever moles of NO should get formed, all those moles should be utilized here. Now, 2 moles should produce 2 moles. 1 mole should produce 1 mole. So 10 moles of NO should produce 10 moles of NO2. So 10 moles of NO2 should produce here, right? Whatever moles of NO2 should produce, that should be utilized here. 3 moles should produce 2 moles. 1 mole should produce 2 by 3. So 10 moles should produce 2 by 3 into 10. So 2 by 3 into 10 moles should be getting produced, which comes out to be 6.66. So 6.66 moles of HNO3 should be getting produced. Should be getting produced, right? So these are the expected moles. These are the expected moles of HNO3. These are the expected moles of HNO3. So reactant was given, product was to be calculated. I got the expected amount of product first. Now multiply this term with the yields. 70%, 50%, 30%. So multiply this term with 0.7 and at the same time multiply it with 0.5. At the same time multiply it with 0.3. 0.3. When you solve this, you'll be getting the value exactly as 0.7. So now these are the actual moles of HNO3 formed. Did you understand what did I do? I calculated the expected moles of HNO3 first, then multiplied that with all the percentage yields together, right? I got the actual moles of HNO3 formed. If you got the actual moles of HNO3 formed, multiply it with the molar mass of HNO3, get the actual mass of HNO3 formed. I hope this sort of a question you will be able to solve from now onwards. This was second method, people. This was second method of solving this question. Okay? Perfect. I hope this much is enough for today, right? Let's end the session with this. And the next session, that's going to be the last session of the chapter mole concept. And that session I'll be taking day after tomorrow. Do not miss that session as well. And I would want you guys to go through this session again, right? Because the types of the questions which I've told you over here, you need to revise them again. Then only you can understand all of them. Okay? Right? And all these questions are not discussed in the one shots, etc., etc. I hope you know that. I hope you know that. So do go through this session again. The next session is going to be day after tomorrow, in which I shall be completing this chapter. So we are just left with percentage purity, percentage composition, and the molecular empirical formula. That's something which I'll be doing in the next session. And do let me know in the comment section if you actually liked this video, because all these questions, I do not think these questions are anywhere on YouTube. Yeah, this is the first time you might be seeing these sort of questions on YouTube. Okay, chalo, take care guys. Bye bye. God bless you all. See you.